Close your eyes for a moment and imagine something with me. Imagine you could ride on a beam of light. Not a car, not a plane, not a rocket, but light itself. The fastest thing in the entire universe. You are sitting on a photon, a tiny packet of energy, hurtling through the vacuum of space at 299,792,458 meters every single second. Let that number sink in. That is not a rough estimate. That is not an approximation. That is the exact speed of light in a vacuum, one of the most precisely measured constants in all of physics. At this speed, you could circle the entire Earth 7.5 times in just 1 second. 1 second. The time it takes you to blink, to snap your fingers, to take a single breath. In that fraction of a heartbeat, light wraps around the entire planet 7.5 times. That is almost incomprehensibly fast. That is the speed that Einstein told us is the absolute cosmic speed limit. Nothing in the universe, no object, no signal, no piece of information can travel faster than this. This is the ultimate speed, the final barrier, the ceiling of the cosmos. And yet, here is the thing that should keep you up at night. Here is the thought that should make you stare at the ceiling at 3 in the morning, questioning everything you thought you knew about the universe. Even at this speed, even at the absolute maximum velocity that the laws of physics allow, you are still too slow. Heartbreakingly, devastatingly, almost cruelly too slow. Too slow to reach most of the galaxies you can see with a telescope. Too slow to explore more than a tiny, tiny fraction of the cosmos. Too slow to ever visit the overwhelming majority of the universe that we know exists. And it is not even close. It is not like you are almost fast enough but just need a little more speed. No. The gap between what light can do and what is required to traverse the universe is so staggering, so enormous, so fundamentally vast that it challenges the very limits of human comprehension. Now, let me ask you something. When you look up at the night sky on a clear, dark evening, far from the city lights, what do you see? You see stars. Thousands of them, scattered across the darkness like diamonds on black velvet. Beautiful, right? Peaceful, serene. But what if I told you that what you are seeing is a lie? Not the stars themselves, no, they are real enough. But what you are seeing is the past. You are looking backward in time, that starlight reaching your eyes right now, at this very moment, left those stars years, decades, centuries, even millennia ago. You are not seeing the universe as it is. You are seeing the universe as it was. And the farther you look, the deeper into the past you see. Some of the light reaching your eyes tonight left its source star before human civilization even existed, before the pyramids were built, before the first humans walked upright on the African savanna. That light has been traveling through the cold, empty void of space for thousands of years, just to reach your retina, just so you could glance up and think, "Oh, pretty stars." And here's what should really twist your mind into knots. Those are just the nearby stars in our own galaxy. When we point our most powerful telescopes at the deep sky, when we peer into the farthest reaches of observable space, we see galaxies. Not just a few, not just hundreds or thousands. We see billions of galaxies, each one containing hundreds of billions of stars, each star potentially surrounded by planets. The sheer scale of what is out there is so far beyond human intuition that no analogy can truly capture it. And the light from those distant galaxies has been traveling not for thousands of years, but for millions, even billions of years. The light from some galaxies we have photographed with the James Webb Space Telescope has been traveling for over 13 billion years. It left its source when the universe was a baby, a mere few hundred million years old, long before our sun existed, long before our galaxy looked anything like it does today, long before Earth was even a possibility. That light has been on a journey across the cosmos for almost the entire history of the universe itself, just to land on the mirror of a telescope floating near our little planet. And here is the cruel twist. Those galaxies, the ones whose ancient light we are collecting, many of them are now so far away that we will never, ever, ever reach them. Not in a human lifetime. Not in 1,000,000 human lifetimes. Not if we had a spacecraft that could travel at the speed of light itself. They are gone. Forever unreachable. And they are getting more unreachable with every passing second. How is that possible? How can something be visible but permanently out of reach? How can we photograph a galaxy but know with mathematical certainty that no spacecraft, no signal, no message from us will ever reach it? That is what we are going to explore today. That is the question at the heart of everything we are about to dive into. And I promise you, by the end of this journey, your understanding of the universe, of space, of time, of distance, and of our place in all of it will be fundamentally transformed. We are going to travel from the very basics of what light is and why it has a speed limit, through the mind-bending scale of the cosmos, into the terrifying reality of an expanding universe, past the invisible walls that imprison us, through the theoretical escape routes that physicists have dreamed up, and finally to the deep, meditative, almost philosophical truth of what it means to be a conscious being in a universe that is, in a very real sense, running away from us. This is going to be a journey, so settle in, get comfortable, and prepare to have your perspective on reality permanently altered. Let us start at the very beginning. What is light? It seems like such a simple question, but the answer is anything but simple. Light is electromagnetic radiation. It is a wave, a ripple in the electromagnetic field that permeates all of space. But it is also a particle, a discrete packet of energy called a photon. This dual nature, this wave-particle duality, was one of the great discoveries of 20th century physics, and it still baffles students and even physicists to this day. Light behaves like a wave when you are not looking at it too closely, spreading out, interfering with itself, creating patterns of bright and dark bands. But when you try to detect it, when you try to measure it, it behaves like a particle, a tiny bullet of energy that hits a detector at a specific point. This is not just a quirk of our measurement instruments. This is a fundamental property of reality itself. Light is genuinely, fundamentally, irreducibly both a wave and a particle at the same time, and any attempt to force it into just one category fails. But here is what matters for our story. A photon, a particle of light, has no mass. Zero. Not a tiny amount, not a negligible amount, but exactly, precisely zero mass. And this is the key to understanding why light travels at the speed it does. In Einstein's theory of special relativity, which he published in 1905 in one of the most revolutionary papers in the history of science, the speed of light emerges not as just the speed of some particular thing called light, but as a fundamental property of space-time itself. It is the speed at which causality propagates. It is the speed at which any massless particle must travel. It is the speed at which information itself can move through the fabric of reality. Light does not accelerate to its speed. It does not start slow and build up. A photon is born at the speed of light. The instant it comes into existence, it is already traveling at 299,792 kilometers per second. It has no choice. The laws of physics demand it. A massless particle must travel at exactly this speed, no more, no less. And a massive particle, anything with even the tiniest speck of mass, can never reach this speed, no matter how much energy you throw at it. Why? Because of the relationship between energy, mass, and velocity that Einstein uncovered. As you accelerate an object with mass, as you push it faster and faster, something strange happens. Its relativistic mass increases. The faster it goes, the heavier it effectively becomes. And as it approaches the speed of light, its effective mass increases without limit, approaching infinity. To push an infinite mass to the speed of light, you would need infinite energy. And infinite energy does not exist. It cannot exist. The total energy content of the entire observable universe is finite. So, no matter how powerful your engine, no matter how advanced your technology, no matter how far into the future you project, if your spacecraft has mass, and any physical spacecraft must have mass, it can never reach the speed of light. It can get close. It can get tantalizingly, agonizingly close. It can reach 99% of light speed. 99.9%. 99.9999%. But that last infinitesimal gap between almost light speed and actual light speed is an unbridgeable chasm that requires more energy than exists in the entire cosmos. This is not an engineering limitation. This is not a technology problem that future civilizations will solve. This is a fundamental law of nature, as inviolable as the law that says you cannot create energy from nothing, as certain as the law that says entropy always increases. The speed of light is the universe's hard speed limit, and there are no exceptions for cleverness. Now, let me give you some perspective on just how fast light is in contexts that might feel more intuitive. We already said light circles the Earth 7.5 times per second, but let us go further. The Moon, our closest celestial neighbor, is about 384,000 kilometers away. Light covers that distance in 1.28 seconds, just over 1 second. When astronauts on the Apollo missions talked to mission control, there was about a 2.5 second round-trip delay. That does not seem like much, right? But now, let us stretch our cosmic legs a little bit. The Sun is about 150 million kilometers from Earth. Light takes 8 minutes and 20 seconds to travel that distance. Think about that. The sunlight warming your face, the sunlight making the plants grow, the sunlight that powers virtually all life on Earth. That light left the Sun over 8 minutes ago. You are not seeing the Sun as it is right now. You are seeing the Sun as it was 8 minutes and 20 seconds in the past. If the Sun suddenly vanished, poof, gone, we would not know for over 8 minutes. We would still see it shining. We would still feel its warmth. For 8 minutes and 20 seconds, we would be completely oblivious to the fact that our star had disappeared. And then, 8 minutes and 20 seconds later, the sky would go dark. And about the same time, we would drift off our orbital path, because gravitational effects also propagate at the speed of light. That is how far away even our own star is. Mars, the planet we dream of colonizing, is between 55 million and 400 million kilometers from Earth, depending on where both planets are in their orbits. At its closest, light takes about 3 minutes to reach Mars. At its farthest, about 22 minutes. This means that when we drive a rover on Mars by remote control from Earth, every command we send takes at minimum 3 minutes to arrive, and every response takes another 3 minutes to come back. A 6-minute round trip at the speed of light, just to the next planet over. If the rover is about to drive off a cliff, we would not know until 3 minutes after it happened, and our emergency stop command would not arrive until 3 minutes after that. This is why Mars rovers have to be semi-autonomous. The speed of light, fast as it is already creating practical problems just within our own solar system. Jupiter, the largest planet in our solar system, is about 778 million kilometers from the Sun. Light from the Sun takes about 43 minutes to reach Jupiter. Saturn? About 79 minutes. Uranus? About 2 hours and 40 minutes. Neptune? Over 4 hours. And Pluto, at the outer edges of what most people think of as our solar system, is about 5.5 light hours away. But the solar system does not end at Pluto. Not even close. The Oort cloud, the vast spherical shell of icy objects that surrounds our solar system, extends to about 1 to 2 light years from the Sun. Light years. Light takes 1 to 2 years just to reach the edge of our own solar system. Already, at the very doorstep of interstellar space, light speed is starting to feel slow, and we have not even left home yet. The nearest star to our Sun is Proxima Centauri, a small red dwarf star that is part of the Alpha Centauri triple star system. It is about 4.24 light-years away. That means light, traveling at 300,000 kilometers per second, takes 4 years and about 3 months to reach our nearest stellar neighbor. 4 years. If you sent a radio message to any potential civilization around Proxima Centauri, and they responded immediately, you would not get a reply for about 8.5 years. A conversation with our nearest neighbors in the galaxy would take nearly a decade per exchange. And Proxima Centauri is absurdly close by cosmic standards. It is literally the star next door, the closest thing to a neighbor we have. Now, let me put this in terms of human technology, because I think this really drives home the point. The fastest object humanity has ever built is the Parker Solar Probe, which reached speeds of about 635,000 kilometers per hour as it swooped close to the Sun. That is incredibly fast by human standards. It could cross the entire United States in about half a minute. But at that speed, how long would it take to reach Proxima Centauri? The answer is about 6,700 years. Nearly 7,000 years. That is longer than all of recorded human history. When this probe arrived at Proxima Centauri, whatever civilization launched it would be ancient history, dust, archaeological ruins, and that is the nearest star. A single star, 4 light-years away. How about the Voyager 1 spacecraft? Launched in 1977, Voyager 1 is the farthest human-made object from Earth. It has been traveling for almost 5 decades now, racing through interstellar space at about 61,000 kilometers per hour. How far has it gotten? About 23 billion kilometers from Earth. That sounds like a lot, until you realize that Proxima Centauri is about 40 trillion kilometers away. Voyager 1 has covered about 0.06% of the distance to our nearest star. If Voyager 1 were heading toward Proxima Centauri, which it is not, it would take about 73,000 years to get there. 73,000 years. Modern humans have only existed for about 300,000 years. Civilization is only about 10,000 years old. Voyager would need 7 times the entire span of human civilization just to reach the star next door. Are you starting to see the problem? Are you beginning to feel, deep in your gut, the immensity of the distances involved? Because we are still talking about our immediate neighborhood. We have not even begun to discuss our galaxy, let alone other galaxies. We are still standing in the cosmic driveway, and already the distances are breaking our brains. Let me take you on a tour of scale now, and I want you to really try to feel each step as we zoom out, because each step is going to multiply the distances by factors of thousands or millions, and your mind is going to resist it. Your brain evolved to understand distances measured in meters and kilometers. It evolved to navigate the African savanna, to judge how far away a predator was, to estimate how long it would take to walk to the next watering hole. It did not evolve to comprehend distances measured in light years or megaparsecs. So, Every step of this journey is going to require a conscious effort to grasp, and I want you to make that effort, because the payoff is a deeper understanding of reality than most people will ever achieve. Our cosmic address starts, of course, with Earth, a small rocky planet orbiting a medium-sized yellow star in the outer suburbs of a spiral galaxy. Our solar system consists of the Sun and everything gravitationally bound to it. 8 planets, their moons, dwarf planets, asteroids, comets, and the Oort cloud. The entire solar system, from the Sun to the outer edge of the Oort cloud, is about 2 light-years across. That is our home, our immediate cosmic neighborhood. Step outside that, and you enter interstellar space, the vast emptiness between stars. Our Sun, along with its solar system, is located in a region called the Orion Arm, one of the smaller spiral arms of our galaxy, the Milky Way. The Milky Way is a barred spiral galaxy, a magnificent pinwheel of stars, gas, dust, and dark matter, spinning slowly through the cosmos. How big is it? The disk of the Milky Way is about 100,000 light-years in diameter. Let me say that again. 100,000 light-years across. Light, traveling at the fastest speed possible, takes 100,000 years to cross from one side of our galaxy to the other. That is 1,000 times longer than all of recorded human history. That is 500 times longer than the existence of Homo sapiens. That is 1/3 of the time since the dinosaurs went extinct. Just to cross one galaxy, our home galaxy, and the Milky Way is not even a particularly large galaxy. It is average, maybe slightly above average. There are galaxies out there that are millions of light-years across, but we will get to that. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number is itself staggering, a range of 300 billion stars that we are not sure about. Each of those stars is, on average, several light-years from its nearest neighbor. Our Sun is about 26,000 light-years from the center of the Milky Way, tucked away in a relatively quiet suburban neighborhood of the galaxy. If you wanted to visit the center of our galaxy, the supermassive black hole called Sagittarius A star that lurks there with a mass of 4 million suns, you would need to travel 26,000 light-years. At light speed, that is 26,000 years. At Voyager speed, about 468 million years, nearly 500 million years just to reach the center of our own galaxy. And the Milky Way is just one galaxy among many. Our galaxy is part of a small collection of galaxies called the Local Group. The Local Group contains more than 54 galaxies, including 2 other major spirals, the Andromeda Galaxy, also known as M31, and the Triangulum Galaxy, also known as M33. The rest are smaller dwarf galaxies, satellite galaxies orbiting the larger ones. The Andromeda Galaxy is the nearest large galaxy to us, and it is 2.5 million light-years away. 2.5 million light-years. Light from Andromeda that is entering your telescope tonight left that galaxy 2.5 million years ago. When that light began its journey, there were no humans on Earth. Our ancestors were Australopithecus, small, ape-like hominids just beginning to walk upright on the African plains. The entirety of human evolution, from those earliest hominids to you reading this right now, has occurred in the time it took that light to travel from Andromeda to here. And Andromeda is the nearest major galaxy. It is the closest big neighbor we have. Beyond the Local Group, the distances become truly staggering. The Virgo cluster, the nearest large galaxy cluster, is about 54 million light-years away. It contains over 1,000 galaxies. 54 million light-years. Light from the Virgo cluster has been traveling since before the dinosaurs went extinct. The Coma cluster is about 321 million light-years away. the Perseus cluster, about 240 million light-years. The Shapley supercluster, one of the most massive concentrations of galaxies in the observable universe, is about 650 million light-years away. And we have not even scratched the surface. The observable universe has a radius of about 46.5 billion light-years. Its diameter is about 93 billion light-years. Now, wait. You might have caught something there that does not seem right. If the universe is 13.8 billion years old, and nothing can travel faster than light, how can the observable universe be 93 billion light-years across? Should not it be, at most, 27.6 billion light-years across, 13.8 billion in each direction? This apparent contradiction is one of the most common sources of confusion in cosmology, and it gets right to the heart of why the speed of light is too slow to reach other galaxies. The answer lies in the expansion of space itself, and this is where our story takes its most dramatic turn. The universe is expanding, not into something, not like a balloon expanding into the room around it, but in a far stranger, far more fundamental way. Space itself is stretching. The very fabric of reality, the arena in which everything exists and happens, is growing, expanding, creating more of itself with every passing moment. This is not metaphor. This is not poetry. This is measurable, observable, quantifiable physical reality, and it changes everything. The story of how we discovered the expansion of the universe is one of the great detective stories in the history of science. It begins in the early 20th century, when astronomers started using spectroscopy to analyze the light from distant celestial objects. When you pass light through a prism, it spreads out into a rainbow of colors, a spectrum. And embedded in that spectrum are specific lines, specific frequencies of light that are absorbed or emitted by particular elements. Hydrogen, helium, oxygen. Each element leaves a unique fingerprint of spectral lines. By studying these lines in the light from distant stars and nebulae, astronomers could determine what those objects were made of, but they noticed something peculiar. In the light from distant galaxies, the spectral lines were shifted. They were not in their usual positions. They were displaced toward the red end of the spectrum. This is called redshift, and it is caused by the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched when it is coming toward you and lower-pitched when it is moving away. When a source of light is moving away from you, the light waves get stretched out, and their frequency decreases, shifting the light toward the red end of the spectrum. The fact that distant galaxies showed redshift meant they were moving away from us. In the 1910s and 1920s, the American astronomer Vesto Slipher measured the spectra of numerous spiral nebulae, which we now know to be galaxies, and found that the vast majority of them were redshifted. They were all moving away from us. This was a strange and puzzling observation. Why would so many objects be moving away from us? Were we at the center of some great cosmic explosion? Then came Edwin Hubble. In 1929, using the powerful new telescope at Mount Wilson Observatory in California, Hubble made one of the most important discoveries in the history of science. He found that the redshift of a galaxy, and therefore its speed of recession, was directly proportional to its distance from us. The farther away a galaxy was, the faster it was moving away. This relationship is now known as Hubble's law, and it can be expressed with a simple equation. Velocity equals the Hubble constant times distance. The Hubble constant, usually denoted h0, tells us the rate at which the universe is expanding. Its current best measured value is about 70 kilometers per second per megaparsec. A megaparsec is a unit of distance equal to about 3.26 million light-years. So what Hubble's law says is this: For every megaparsec, every 3.26 million light-years of distance between us and a galaxy, that galaxy is moving away from us 70 kilometers per second faster. Let us work through some numbers to really feel this. A galaxy that is 1 megaparsec away, about 3.26 million light-years, is receding from us at 70 kilometers per second. That is fast, about 252,000 kilometers per hour, but it is only 0.023% of the speed of light. No problem. A galaxy 10 megaparsecs away, about 32.6 million light-years, is receding at 700 kilometers per second. Still manageable. A galaxy 100 megaparsecs away, about 326 million light-years, is receding at 7,000 kilometers per second. That is about 2.3% of the speed of light. Getting faster. A galaxy 1,000 megaparsecs away, about 3.26 billion light-years, is receding at 70,000 kilometers per second. That is about 23% of the speed of light. Now we are talking some serious speed, and a galaxy at a distance of about 4,280 megaparsecs, roughly 14 billion light-years, is receding at 300,000 kilometers per second. The speed of light, and anything beyond that distance is receding from us faster than the speed of light. Stop. Read that last sentence again. Galaxies beyond about 14 billion light-years are receding from us faster than the speed of light. How is that possible? Did we not just say, did Einstein not prove that nothing can travel faster than light? This is the crucial, absolutely essential distinction that lies at the very core of this entire topic. And if you understand this one thing, you will understand why the speed of light is too slow to reach other galaxies. So let me be very, very clear about what is happening. Einstein's theory of special relativity says that nothing can move through space faster than the speed of light. Through space, an object, a spaceship, a particle, a signal, cannot travel through the fabric of space-time at a velocity exceeding the speed of light. That law is inviolable. That law is ironclad. That law, as far as we know, has no exceptions. But there is a loophole, a cosmic loophole, and the universe exploits it ruthlessly. The loophole is this: space itself can expand at any rate whatsoever. There is no speed limit on the expansion of space. Space is not a thing that moves through space. Space is the arena. It is the stage, and the stage can grow as fast as it wants. When we say that a distant galaxy is receding from us faster than the speed of light, we do not mean that the galaxy is flying through space faster than light. The galaxy might be sitting perfectly still with respect to its local space. What is happening is that the space between us and that galaxy is expanding, stretching, growing, and it is doing so at a rate that, when you add up all the expansion across that vast distance, results in the total distance between us increasing faster than light can travel across it. It is not the galaxy that is moving faster than light. It is the space between us that is growing faster than light. The analogy I want you to hold in your mind is this. Imagine a balloon, a big rubber balloon, and on the surface of this balloon you draw little dots with a marker. These dots represent galaxies. Now start inflating the balloon. What happens to the dots? They all move apart from each other, not because the dots are sliding across the rubber surface, but because the rubber surface itself is stretching. The dots are fixed to the rubber, they are not going anywhere, but the expansion of the rubber between them carries them apart. And here is the key. Two dots that are very close together move apart slowly, because there is only a little bit of rubber between them to expand. But two dots on opposite sides of the balloon move apart very quickly, because there is a lot of rubber between them, and all of it is expanding. The more rubber between two dots, the faster they separate. That is Hubble's law in a nutshell. That is why more distant galaxies recede faster. But the balloon analogy has a weakness, and I want to address it, because I think it is important for building an accurate picture. A balloon is a two-dimensional surface expanding in three-dimensional space. You can see the balloon from the outside, you can see that it has a center, that it is expanding outward. But the universe is not like that. The universe, as far as we can tell, does not have an edge, does not have a center, and is not expanding into anything. It is expanding in itself. Every point in the universe sees every other point moving away. There is no center of the expansion. If you could teleport to the most distant galaxy we have ever observed and set up a telescope there, you would see all the other galaxies moving away from you, just as we see them moving away from us. You would think you were at the center, and you would be just as right and just as wrong as we are. Because there is no center. The expansion is happening everywhere, at every point in space, simultaneously. This is conceptually challenging, I know. It is one of those things where the math is crystal clear, but the intuition fails, because we evolved in a small, flat, non-expanding patch of space-time, and our brains just do not have the built-in machinery to intuitively grasp what it means for space itself to be expanding. But the math works. The observations confirm it. This is how the universe operates, whether our intuitions can keep up or not. Now, let us talk about what is driving this expansion, because this is where the story gets even more dramatic. For decades after Hubble's discovery, cosmologists assumed that the expansion of the universe must be slowing down. After all the matter in the universe attracts all the other matter through gravity. Every galaxy is pulling on every other galaxy. This gravitational attraction should be acting as a brake on the expansion, gradually decelerating it. The big question in cosmology throughout the latter half of the 20th century was whether this gravitational braking was strong enough to eventually stop the expansion and cause the universe to collapse back in on itself. A scenario called the Big Crunch, or whether the expansion would slow down but never quite stop, with the universe expanding forever, but at an ever-decreasing rate. In 1998, two teams of astronomers set out to measure how much the expansion was decelerating by studying distant Type 1a supernovae. Type 1. A supernovae are a special kind of stellar explosion that occurs when a white dwarf star accumulates too much mass from a companion star and undergoes a catastrophic thermonuclear detonation. The crucial thing about these supernovae is that they all have roughly the same intrinsic brightness. They are what astronomers call standard candles. Because you know how bright they actually are, you can compare that to how bright they appear, and from the difference, you can calculate how far away they are. By measuring both the distance and the redshift of these supernovae at various distances, the astronomers could map out the history of the universe's expansion rate. What they found shocked the world. The expansion of the universe was not decelerating. It was accelerating. The expansion was not slowing down. It was speeding up. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been if the expansion were slowing. Something was pushing the universe apart, counteracting gravity, and it was winning. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, and it sent shockwaves through the entire field of cosmology. There was some mysterious force, some unknown energy, pervading all of space and driving the universe apart at an ever-increasing rate. They called it dark energy, and it remains one of the deepest mysteries in all of science. Here is what we know about dark energy. It makes up about 68% of the total energy content of the universe. 68%. The vast majority of everything that exists is this mysterious stuff, and we have no idea what it is. We know what it does. It pushes space apart. It causes the expansion to accelerate. It acts like a negative pressure, a kind of anti-gravity that operates on cosmic scales. One leading candidate for what dark energy might be is the cosmological constant, a term that Einstein actually introduced into his equations of general relativity in 1917, because he believed the universe was static and needed a term to counterbalance gravity. When Hubble discovered the expansion, Einstein reportedly called the cosmological constant his greatest blunder, because it turned out the universe was not static and he had introduced the term for the wrong reasons. But now, decades later, it turns out there might indeed be something very much like a cosmological constant at work. Sometimes the universe has the last laugh. But regardless of what dark energy actually is, its effects are devastating for any hopes of intergalactic travel. Because the expansion of the universe is accelerating, the rate at which distant galaxies recede from us is increasing over time. The speed at which space is stretching is not constant. It is growing. This means that galaxies that are currently receding from us faster than light are going to recede even faster in the future, and galaxies that are currently just barely reachable by light are going to slip beyond the reachable threshold. The unreachable part of the universe is growing. The prison walls are closing in. Let me introduce you to one of the most important and haunting concepts in all of cosmology, the cosmic event horizon. You may have heard of the event horizon of a black hole. It is the boundary around a black hole beyond which nothing, not even light, can escape. Once you cross the event horizon, you are doomed to fall into the singularity. There is no coming back. Well, the universe has its own version of an event horizon, and it works in a disturbingly similar way. The cosmic event horizon is the boundary beyond which light emitted today, right now, at this very moment, will never reach us. Not because there is not enough time, but because the expansion of space between here and there will always outpace the light. The light will travel toward us at 300,000 kilometers per second, but the space it is traveling through will be expanding faster than that, and the light will be swept backward, carried away by the expanding tide of space, never to arrive. It is like trying to swim toward shore in a river that flows faster than you can swim. No matter how hard you paddle, the current carries you away. You never reach land. That is what is happening to light from galaxies beyond our cosmic event horizon. The cosmic event horizon is currently at a co-moving distance of about 16 billion light-years. Any galaxy currently farther than about 16 billion light-years from us is beyond our cosmic event horizon. Light that we emit today will never reach that galaxy. And light that galaxy emits today will never reach us. We are permanently, irrevocably cut off from each other. And here is the truly heartbreaking part. This is not a static boundary. Because the expansion is accelerating, the cosmic event horizon is, in a sense, shrinking. Over time, more and more galaxies are being carried beyond this threshold. Galaxies that are reachable today will not be reachable tomorrow. Every second, every moment, the universe is slipping away from us. A little more of it passing beyond the cosmic event horizon, a little more of it lost forever. But wait, it gets even more confusing and more profound. There is a difference between the cosmic event horizon and what we call the observable universe. The observable universe is much larger than the cosmic event horizon. The observable universe has a radius of about 46.5 billion light-years, but the cosmic event horizon is only about 16 billion light-years. So how can we see things beyond the cosmic event horizon? Because the observable universe is defined by light that was emitted in the past, when the universe was smaller, when those galaxies were closer. The light from those distant galaxies has been traveling for billions of years, and during that time, space has been expanding. carrying those galaxies farther and farther away. The galaxies that emitted that light are now far beyond the cosmic event horizon, far beyond the distance that light emitted today could ever bridge. But their ancient light, emitted eons ago when they were closer, has been slowly trudging toward us through the expanding space, and it is just now arriving. We are seeing those galaxies as they were billions of years ago, in a smaller, younger, more compact universe. They are ghosts, echoes, light fossils. We see their past, but their present is forever hidden from us, and their future is completely and permanently beyond our reach. Let me give you a specific example that I think really drives this home. The James Webb Space Telescope has observed galaxies at redshifts of 14 and beyond. One of the most distant confirmed galaxies, known as JADES-GS-Z 14-O, has a redshift of about 14.32. This means we are seeing it as it existed approximately 290 million years after the Big Bang, when the universe was a mere toddler. The light from this galaxy has been traveling through space for about 13.5 billion years to reach us. But because space has been expanding the entire time that light was in transit, the galaxy itself is now about 33 billion light-years away from us. 33 billion light-years. Even though the light has only traveled for 13.5 billion years, the galaxy is now much farther than that, because the space the light was traveling through was stretching out behind it as it moved. And this galaxy is almost certainly beyond our cosmic event horizon now. Light we emit today will never reach it. It is gone. What we see is a snapshot from the dawn of time, the last message in a bottle from a galaxy that is now so far away, moving away so fast that we will never hear from it again. Now, I want to take a moment here because I think this idea deserves space to breathe. I think we need to really sit with this, really feel the weight of it, because it is one of the most profound and unsettling truths about the universe we live in. We can see galaxies that we will never visit. We can photograph galaxies that we can never send a message to. We can study the physics, the chemistry, the history of galaxies that are forever beyond our reach. We have more knowledge than access. We have more sight than mobility. The universe has given us the eyes of an eagle, but the wings of a penguin. We can see the mountaintop, but we can never climb it. And it is not because we are not clever enough or not technologically advanced enough. It is because the fundamental laws of physics, the laws of relativity and the expansion of space, make it literally, physically, mathematically impossible. This is not a problem to be solved. It is a condition of existence to be understood and, in some way, accepted. Let me talk about numbers now, real numbers. Because I think when you see the actual time spans involved in trying to reach other galaxies, even at the speed of light, the full magnitude of the problem becomes undeniable. Let us start with a manageable one. Our nearest large galaxy, the Andromeda Galaxy, is 2.5 million light-years away. If you could somehow build a spacecraft that could travel at the speed of light, the absolute maximum speed the universe allows, it would take 2.5 million years to get there. 2.5 million years. Let us put that in context. 2.5 million years ago, the genus Homo had just appeared on Earth. Our ancestors were using the most primitive stone tools. They had brains about a third the size of ours. They could not speak, could not write, could not build. The entire saga of human evolution, from Homo habilis to modern civilization, from stone tools to smartphones, from caves to cities, from fire to nuclear fusion, that entire epic story of our species fits within the time it would take light to reach Andromeda. And that is the closest major galaxy. Let us go further. The Sombrero Galaxy, a beautiful and iconic galaxy that looks like a wide-brimmed hat, is about 31 million light-years away. At light speed, 31 million years to get there. 31 million years ago, the continents of Earth were in noticeably different positions. The climate was different. The species that existed then are mostly extinct now. The entire span of time from the extinction of the dinosaurs to the present day is about 66 million years, roughly twice the light travel time to the Sombrero Galaxy. These timescales are not just impractical, they are geologically significant. The giant elliptical galaxy M87, famous for being the home of the first black hole ever directly imaged, is about 55 million light-years away. Light speed to M87, 55 million years. That is about the time since the dinosaurs went extinct. NGC 1277, a massive galaxy in the Perseus cluster, is about 220 million light-years away. At light speed, you would arrive in 220 million years, roughly the time of the first dinosaurs. And I, C1101, one of the largest known galaxies in the universe, a monstrous elliptical galaxy 6 million light-years across, is about 1 billion light-years away. 1 billion years at light speed. A billion years ago, life on Earth was entirely single-celled. Multicellular life had barely begun to experiment with its first tentative forms. The time span from then to now, the entire evolution of complex life on Earth, fits within a light-speed journey to a single galaxy, and these are all galaxies that are, by cosmic standards, relatively nearby. The observable universe is 46.5 billion light-years in radius. The most distant galaxies we can see are already over 30 billion light-years away. At light speed, you would need 30 billion years to reach them. The universe itself is only 13.8 billion years old. You would need more than twice the current age of the universe to reach galaxies that we can already see and photograph. And by the time you got there, assuming the speed of light could somehow be maintained for that absurd duration, those galaxies would have moved even farther away, because space would have been expanding the entire time you were traveling. You would be chasing a target that is constantly running away, and running away faster and faster. It is like trying to catch a train that is accelerating while you are running at constant speed. You will never catch it. Eventually, it will be moving so fast that you will fall further and further behind until it vanishes over the horizon. But there is another problem, one that makes this even more hopeless than the raw numbers suggest. It is the problem of the moving target, and it is deeply insidious. When you look at a galaxy that is, say, 10 billion light-years away, what you are actually seeing is the galaxy as it was 10 billion years ago, in the location it was 10 billion years ago. That galaxy is not there anymore. It has moved, or rather, the expansion of space has carried it much farther away. When you set out on your light-speed journey toward that galaxy, you aim at where it appears to be. But that is where it was, not where it is, and certainly not where it will be when you arrive. By the time your spacecraft reaches the spot where the galaxy used to be, 10 billion years will have passed, and the galaxy will have been carried billions of light-years farther away by the expansion of space. You aimed at a ghost, a phantom, a light echo from the ancient past. And the actual galaxy is now so far away that you are no closer to reaching it than when you started. In fact, you might be further from it than when you began your journey, because the space between you has been expanding the entire time. This is the true cruelty of the expanding universe. It is not just that things are far away, it is that the far away things are getting further away. And they are getting further away faster, and the rate at which they are getting further away faster is itself increasing. It is failure compounded upon failure, wrapped in impossibility, drizzled with mathematical certainty. The expanding universe does not just make intergalactic travel difficult, it makes it, for the vast majority of galaxies, fundamentally and permanently impossible, even at the speed of light. Now, I want to introduce a beautiful but melancholy concept. I want to talk about what the future holds for the universe and for any civilization that exists within it, because the expansion of space is not just a problem for today. It is a problem that gets worse over time, and the long-term consequences are staggering. Today, if you look through a powerful telescope, you can see about 2 trillion galaxies in the observable universe. 2 trillion. That is a lot of galaxies. Each one a vast island of stars, each one a potential home for life, each one a treasure trove of cosmic beauty and mystery. But this will not always be the case. Because the expansion is accelerating, galaxies at the edge of our observable universe are slowly being pushed beyond the cosmic event horizon. Their light is being stretched to longer and longer wavelengths, dimmer and dimmer, redder and redder, until eventually it fades below the threshold of detectability. They do not wink out suddenly. They fade, like a ship sailing over the horizon, its sail growing smaller and dimmer until it vanishes. One by one, the most distant galaxies will disappear from view, and this process has already begun. In about 100 billion years, give or take, the expansion of the universe will have carried every galaxy outside our local group beyond the cosmic event horizon. Every single one. The Virgo cluster, the Coma cluster, the great superclusters and filaments of the cosmic web, all of it will be gone. Not destroyed, mind you. Those galaxies will still exist. Stars will still burn in them. Planets will still orbit. Perhaps civilizations will still thrive. But we will never know because their light will never reach us again. From our vantage point, they will simply cease to exist. Our night sky, or rather the sky seen by whatever civilization inherits our corner of the universe, will contain only the stars of our own galaxy, which by then will have merged with Andromeda and the other members of the local group into a single large elliptical galaxy sometimes fancifully called Milkomeda or Milkdromeda. And here is the truly haunting part. A civilization that arises in that far future, hundreds of billions of years from now, will look out at the universe and see only their own galaxy. They will see no other galaxies. They will have no evidence that other galaxies ever existed. The cosmic microwave background radiation, the faint afterglow of the Big Bang that is currently the strongest evidence for the hot, dense origin of the universe, will have been stretched by the expansion to wavelengths so long that it will be completely undetectable. There will be no Hubble's law to discover, because there will be no visible galaxies to measure receding. There will be no evidence of expansion, no evidence of a Big Bang, no evidence that the universe was ever any different from the dark, lonely, apparently static cosmos they inhabit. Think about that for a moment. Those future scientists, presumably as brilliant as ours, using their best instruments and their sharpest theories, would construct a picture of the universe that is completely, fundamentally wrong. They would conclude that the universe consists of a single galaxy floating in an infinite, empty, static void. They would have no way of knowing about the trillions of galaxies that once filled the sky. They would have no way of discovering the expansion, the Big Bang, the cosmic microwave background, the large-scale structure. All of that evidence will have been erased by the very expansion that it once testified to. The universe will have covered its tracks. The greatest story ever told, the story of the birth and evolution of the cosmos, will be hidden, sealed away behind an impenetrable wall of expanding space. We are living in a special time. Right now, today, we can still see the evidence. We can still detect the cosmic microwave background. We can still observe the expansion. We can still photograph distant galaxies and map the large-scale structure of the cosmos. We are living in the brief window of cosmic time when the universe is still revealing its secrets. That window is closing, slowly but inexorably, and future generations may never know what we know. In some profound sense, we are the universe's witnesses. We are the ones who get to see the full picture, or at least more of it than anyone who comes after us. That is a privilege, and it is also a responsibility. Let me return now to the physics, because there is another fascinating and counterintuitive aspect of traveling at or near the speed of light that I want to explore. It is called time dilation, and it is one of the strangest predictions of Einstein's special relativity. It is also, at first glance, a potential loophole in the problem of intergalactic distances. But as we will see, it is a bittersweet loophole at best. Time dilation is this. As you travel faster and faster, approaching the speed of light, time passes more slowly for you relative to someone who is at rest. This is not a trick. This is not an illusion. This is a real, physical effect that has been confirmed experimentally countless times, from particle accelerators where short-lived particles last much longer than expected because they are moving so fast, to atomic clocks flown on airplanes that return measurably behind identical clocks left on the ground. Time really does slow down when you move fast, and the closer you get to the speed of light, the more extreme the effect becomes. The formula for time dilation is elegant and simple. The time experienced by the traveler equals the time experienced by the stationary observer, multiplied by the square root of 1 minus the velocity squared divided by the speed of light squared. At 50% of the speed of light, the traveler's clock runs at about 87% of the normal rate. Not a huge difference. At 90% of the speed of light, the traveler's clock runs at about 44% of the normal rate. Now we are talking. At 99% of the speed of light, the traveler's clock runs at about 14% of the normal rate. 7 years of travel feels like 1 year for the traveler. At 99.99% of the speed of light, time slows to about 1.4%. 100 years of travel feels like 1.4 years. And at 99.9999% of the speed of light, 100 years of travel feels like only a few days. So, here's the tantalizing thought experiment. What if you could build a spacecraft that could travel at 99.9999% of the speed of light? Could you use time dilation to effectively cheat the vast distances? Could you, as a passenger, experience a relatively short journey to Andromeda, even though it is 2.5 million light-years away? The math says, kind of, at 99.99% of the speed of light, you would experience the trip to Andromeda in about 35,000 years of subjective time. That is still enormously long, longer than civilization itself, but it is a lot less than 2.5 million years. At 99.9999% of light speed, you might experience it in only a few thousand years. And at speeds absurdly, impossibly close to light speed, the subjective travel time could, in theory, be reduced to years, months, or even less. There is a related effect called length contraction. At speeds approaching light, distances in the direction of travel shrink from the traveler's perspective. The faster you go, the shorter the distance appears. At 99.9999% of light speed, the distance to Andromeda would appear to shrink to perhaps a few thousand light-years in your frame of reference. The universe literally compresses in front of you. You are not traveling less distance in some absolute sense. The distance is genuinely, physically shorter in your reference frame. This is one of the most counterintuitive predictions of special relativity, and it is absolutely real. So, is this the answer? Can time dilation and length contraction save us? Can we use the weirdness of relativity to effectively tunnel through the vast distances of intergalactic space? Unfortunately, no. And there are several reasons why. First, there is the energy problem. To accelerate a spacecraft to 99.9999% of the speed of light requires an absurd amount of energy. Remember, as you approach light speed, your relativistic mass increases without limit. The energy required to accelerate even a modest spacecraft to such speeds would be staggeringly enormous, far beyond anything our civilization can produce, far beyond what seems feasible even for a civilization vastly more advanced than ours. We are talking about energy requirements on the order of the total energy output of stars for a single spacecraft. Second, there is the practical problem of duration. Even with extreme time dilation, the journey time is still thousands of years for the traveler and millions of years for the rest of the universe. No known material can withstand the rigors of space travel for thousands of years without maintenance. Radiation, microparticle impacts, material fatigue, equipment failure, all of these are enormous challenges on timescales of decades, let alone millennia. Third, and this is the really heartbreaking part, even if you somehow made the journey, you could never go home. Not to the home you left. While you experienced thousands of years on your ship, millions of years passed on Earth. Everyone you knew, every civilization you were part of, every culture, language, institution, everything would be gone. Earth itself might be unrecognizable. The sun will still be shining, probably, since it has about 5 billion years of fuel left. But human civilization as you knew it would be ancient history. You would arrive at Andromeda a stranger in time, and if you turned around and came back, millions more years would pass. You would return to an Earth that had moved on without you for millions of years. That is the bitter truth of time dilation. It can make the journey shorter for you, but it cannot make the universe smaller. It cannot undo the vast distances. It just makes you experience them differently, while the rest of reality carries on without you. And fourth, time dilation does nothing about the expansion of space. For galaxies beyond the cosmic event horizon, time dilation is irrelevant. No amount of time dilation can get you to a galaxy that is receding faster than light. You can slow your clock to a crawl, but if the space between you and your destination is expanding faster than you are moving through it, you will never arrive. You will fall further and further behind, and no amount of relativistic trickery will change that. There is one more aspect of time dilation that I want to share, because I think it is profoundly beautiful and strange. Consider the photon itself. A photon traveling at the speed of light experiences infinite time dilation. Its clock does not just slow down, it stops entirely. From the photon's perspective, if we can even meaningfully talk about a photon's perspective, no time passes at all. Not a tiny amount. Zero. A photon that travels from a distant galaxy to your telescope, a journey of billions of years in our frame, experiences the entire trip as instantaneous. Emission and absorption are the same event for the photon. It exists in a frozen moment, a single instant that, from our perspective, spans billions of years and billions of light years. The photon does not experience the journey. It does not experience the vast emptiness of intergalactic space. It does not experience the billions of years of travel. For the photon, there is no journey. There is only departure and arrival, and they are the same thing. This is almost mystical in its strangeness. The light that has traveled 13 billion years across the cosmos to reach the mirror of the James Webb Space Telescope. That light did not experience a 13 billion year journey. It experienced nothing. It was emitted by a young galaxy in the infant universe, and in the same instant, from its own perspective, It was absorbed by a detector orbiting a small rocky planet around a medium-sized star in a galaxy called the Milky Way. The entire history of the universe, from the photon's point of view, is a single timeless moment. And yet, for us, for the observers, it tells a story of billions of years of cosmic evolution. I want to take us now on a slight detour, not away from our main topic, but into a territory that enriches it, the nature of the space between galaxies. Because when we talk about traveling to other galaxies, we tend to focus on the speed and the distance, but we rarely talk about what lies between. And what lies between is a vast, haunting emptiness that deserves our attention. Intergalactic space is the loneliest place in the universe. Between galaxies, there is almost nothing. The intergalactic medium, as it is called, contains roughly 1 to 10 atoms per cubic meter. Compare that to the air you are breathing right now, which contains about 25 trillion molecules per cubic meter. Intergalactic space is not just empty, it is the emptiest environment in the known universe. It is a void so thorough, so complete, that it makes the vacuum of interstellar space look crowded by comparison. And yet, intergalactic space is not perfectly empty. There is a thin, hot gas called the warm-hot intergalactic medium, which exists at temperatures of hundreds of thousands to tens of millions of degrees. This gas is so sparse that even though it is incredibly hot, you would freeze to death in it, because there is so little matter to transfer heat to your body. It is hot in terms of the kinetic energy of individual particles, but there are so few particles that the total thermal energy is negligible. This gas is part of the cosmic web, the vast, large-scale structure of the universe that connects galaxies like strands in a spider's web. The cosmic web itself is one of the most beautiful structures in the universe. If you could zoom out far enough, far beyond individual galaxies, far beyond galaxy clusters, you would see the universe arranged in a stunning pattern of filaments and voids. Filaments are long, thin strands of galaxies, gas, and dark matter that stretch across hundreds of millions of light years. They connect galaxy clusters to each other in a vast network. And between the filaments are the voids, enormous, nearly empty bubbles of space that can be hundreds of millions of light years across. The Bootes void, for example, is approximately 330 million light-years in diameter and contains almost no galaxies. If you were floating in the center of the Bootes void, you would look out in every direction and see nothing. No stars, no galaxies, no nebulae, just infinite, perfect darkness. The nearest galaxy would be over 100 million light-years away, a faint smudge, barely visible even with the most powerful telescope. You would be more alone than any human being has ever been or ever will be. The isolation would be absolute and complete. Now imagine traveling through this void, not at light speed, which is already inconceivable, but even at light speed. You set out from one side of the Bootes void. 330 million years later, you reach the other side. 330 million years of travel through absolute emptiness. No landmarks, no waypoints, no reference frames except the faint, distant glow of galaxies impossibly far away. 330 million years of solitude. And the Bootes void is just one void among many. The universe is full of them. The KBC void, which some evidence suggests our own galaxy may be inside, is about 2 billion light-years across. 2 billion years of travel through nothingness, even at light speed. These are the deserts of the cosmos, and they make the Sahara look like a puddle. The practical challenges of intergalactic travel, if we ever attempted it, would be staggering. There would be no stars nearby for gravity assists, which are one of the key techniques we use to accelerate spacecraft in our own solar system. There would be no sources of fuel or energy except what you brought with you. There would be no way to communicate with home in any meaningful way. A message sent back to Earth would take millions of years to arrive, and a response would take millions more. By the time you received a reply, the civilization that sent it would be ancient history. There would be no way to repair or replace equipment that broke down. Any repair parts would need to last for millions of years. And there would be the radiation. Cosmic rays, high-energy particles from distant supernovae and active galactic nuclei would constantly bombard the spacecraft. Over millions of years, this radiation would degrade materials, damage electronics, and, for any biological crew, accumulate fatal doses of radiation thousands of times over. The psychological challenges are almost unimaginable. A crew on an intergalactic voyage would be utterly, completely alone in a way that no human has ever experienced. No rescue is possible. No return is possible. No communication with any other living being is possible. The crew would need to sustain a functioning society for thousands of generations, maintaining the knowledge, the skills, the motivation, and the social cohesion necessary to operate a spacecraft for millions of years. Human civilizations on Earth rarely last more than a few centuries without undergoing dramatic transformations. How could a small community on a spacecraft maintain its purpose and functionality for millions of years? It is a challenge that dwarfs any engineering problem. It is a sociological, psychological, and philosophical problem of the highest order. So, where does this leave us? Let us take stock of the situation. The speed of light is the fastest speed possible. But the universe is so vast that even light speed is laughably inadequate for intergalactic travel. The distances are measured in millions and billions of light years. The expansion of space means that most of the universe is receding from us faster than light, and the expansion is accelerating. The cosmic event horizon means that a growing fraction of the universe is permanently beyond our reach. Time dilation can make the journey shorter for the traveler, but cannot undo the real distances or overcome the expansion of space. The voids between galaxies are immense, empty, and hostile, and the practical challenges of sustaining a spacecraft and its crew for millions of years are beyond anything we can currently conceive. Is there any hope? Is there any theoretical possibility that could allow us to overcome these limitations? The answer is a cautious, heavily qualified, but genuine maybe. And to explore it, we need to venture into the realm of speculative physics, where the boundaries between science and science fiction become delightfully blurry. The first possibility, and the one that captures the imagination most vividly, is the warp drive. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that sent ripples through both the physics community and popular culture. Alcubierre asked a simple but brilliant question. Einstein says you cannot travel through space faster than light. But what if you did not travel through space at all? What if, instead, you moved space itself around you? Alcubierre proposed a theoretical mechanism that would compress the space in front of a spacecraft and expand the space behind it. The ship would sit in a bubble of flat, undistorted space-time, completely stationary with respect to its local space. But the bubble itself would move, carried along by the compression and expansion of the surrounding space at any speed, including faster than light. The ship would surf on a wave of space-time, like a surfer riding a wave on the ocean. The surfer does not move through the water. The water moves the surfer. Similarly, the ship would not move through space. Space would move the ship. And since there is no speed limit on the expansion or contraction of space itself, the ship could effectively travel faster than light without violating Einstein's prohibition on faster-than-light travel through space. This is a staggeringly beautiful idea. It is also, currently, staggeringly impractical. Alcubierre's original calculations showed that the warp bubble would require a form of matter with negative energy density, something called exotic matter. Exotic matter is not the same as antimatter, which is perfectly real and well understood. Exotic matter is a hypothetical form of matter that has negative mass or negative energy, and while certain quantum effects like the Casimir effect suggest that negative energy densities might exist in tiny amounts, the quantities required for a warp drive would be absurdly large. Alcubierre's original design required an amount of negative energy equivalent to the total mass energy of the entire observable universe. Later refinements by various physicists reduced this requirement, first to the mass energy of the planet Jupiter, then to smaller amounts. But even the most optimistic estimates require enormous quantities of a substance that we do not know how to produce, contain, or control. There are other problems too. Harold White at NASA's Eagle Works laboratory worked on ideas to further reduce the energy requirements and even claimed to have detected a tiny warp field effect in laboratory experiments, though these results were highly controversial and have not been independently confirmed. More recently, in 2021, Eric Lentz published a paper proposing warp drive solutions that might work with positive energy only, eliminating the need for exotic matter entirely. And Alexei Bobrik and Johnny Martyr have worked on classifying different types of physical warp drives and exploring their properties. These are exciting developments, but they are very early-stage theoretical work. We are still a very, very long way from anything that could be built or tested, if it is even possible at all. And there are deeper theoretical concerns. A warp drive might create causal paradoxes. If you can travel faster than light, you can, in principle, travel backward in time. This is because of the way special relativity connects space and time. Faster than light travel, if achieved by any means, creates the possibility of closed time-like curves, which are just a fancy way of saying time loops. You could arrive at your destination before you left. You could create paradoxes, like the classic grandfather paradox, where you go back in time and prevent your own birth. Many physicists believe that the laws of nature must somehow prevent this, a principle called the chronology protection conjecture, proposed by Stephen Hawking, who half-jokingly said that the universe must have a chronology protection agency that prevents time travel. If Hawking is right, then there might be some deep law of physics that prevents warp drives from working, even if the mathematics seems to allow them. There is also the problem of what happens at the boundary of the warp bubble. Some calculations suggest that the bubble would accumulate extremely high-energy particles at its front edge, creating a devastating blast of radiation that would be released at the destination when the bubble decelerates. You would arrive at your target galaxy only to destroy everything in your path with a burst of gamma radiation. Not exactly a friendly way to introduce yourself to the neighbors. The second major theoretical possibility for faster-than-light travel is the wormhole, also known as an Einstein-Rosen bridge. Wormholes are solutions to the equations of general relativity that connect two distant points in space-time via a shortcut, a tunnel through the fabric of reality itself. Imagine folding a piece of paper so that two distant points touch, and then poking a hole through both layers. Instead of traveling along the surface of the paper from one point to the other, which would take a long time, you just step through the hole and instantly arrive at the other side. That is, very roughly, what a wormhole would do. Wormholes were first theorized by Albert Einstein and Nathan Rosen in 1935, hence the name Einstein-Rosen bridges. However, their version of a wormhole was not traversable. It would pinch off and collapse faster than anything. Even light could pass through it. It was a mathematical curiosity, not a practical shortcut. In 1988, the physicist Kip Thorne working with his students, explored the conditions under which a wormhole might be held open long enough for something to pass through. They found that it would require exotic matter, the same kind of negative energy material needed for the Alcubierre warp drive. The exotic matter would need to thread the throat of the wormhole, propping it open against its natural tendency to collapse. Without the exotic matter, the wormhole slams shut in an instant, far too fast for anything to traverse it. As with the warp drive, the practical obstacles are immense. We have never observed a wormhole. We have no evidence that naturally occurring wormholes exist anywhere in the universe. If they do exist, they are likely microscopic, far too small for any macroscopic object to pass through. Creating a macroscopic, traversable wormhole would require technology so far beyond anything we can currently imagine that it barely qualifies as speculative. And even if we could create one, we would need to somehow move one end of it to the target destination. But moving one end to another galaxy requires crossing the very distance we are trying to shortcut. It is a chicken and egg problem of the highest order. You need a wormhole to get to the other galaxy, but you need to get to the other galaxy to set up the wormhole. There is a fascinating theoretical connection between wormholes and quantum mechanics that has emerged in recent years. In 2013, Juan Maldacena and Leonard Susskind proposed a conjecture known as ER equals EPR, which suggests that Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen pairs, quantum entangled particles. In other words, every pair of entangled particles might be connected by a tiny, microscopic wormhole. This is a breathtaking idea that connects general relativity and quantum mechanics in a deep and unexpected way. If it is correct, it might eventually lead to new insights about how to create or manipulate wormholes. But we are a very, very long way from turning this theoretical insight into practical technology. Speaking of quantum entanglement, let me address a common misconception. Many people have heard that quantum entanglement allows instantaneous communication across any distance, and they wonder whether this could solve the intergalactic communication and travel problem. Unfortunately, it cannot. Quantum entanglement is real and has been experimentally verified many times. When two particles are entangled, measuring the state of one instantly determines the state of the other, no matter how far apart they are. This does appear to be instantaneous, and Einstein famously called it spooky action at a distance. But here's the crucial point. No information can be transmitted via entanglement. The outcome of each individual measurement is random. You cannot control what result you get. You cannot encode a message in the entanglement. You can only discover, after the fact by comparing notes through a conventional communication channel, that the measurements are correlated. This is proven by the no communication theorem, a mathematical result that shows that quantum entanglement cannot be used to send information faster than light. Entanglement is a correlation, not a communication channel. It is like having two sealed envelopes, one containing a red card and one containing a blue card. Opening one envelope tells you instantly what is in the other, no matter how far apart they are. But no information was transmitted. The correlation was established when the envelopes were sealed, not when they were opened. Entanglement works the same way. It is fascinating. It is useful for certain things like quantum encryption and quantum computing, but it is not a faster-than-light communication device. Let me explore some other theoretical and speculative approaches to intergalactic travel. One idea that has been around for a long time is the generation ship. The concept is simple in principle. Build a massive spacecraft, large enough to support a self-sustaining community, and send it on its way. The original crew would live, work, reproduce, and die on the ship. Their children would grow up on the ship. Their children's children would grow up on the ship. and so on, generation after generation, for as long as the journey takes. The ship is not just a vehicle, it is a world, a self-contained civilization hurtling through the void. For interstellar travel, this concept is at least imaginable. A generation ship traveling at even a fraction of a percent of light speed might reach nearby stars in thousands of years, spanning maybe 100 generations or so. It is a staggering undertaking, but it is not obviously impossible. Human civilizations have, after all, lasted for thousands of years, and a sufficiently well-designed generation ship might be able to sustain itself for similar periods. But for intergalactic travel, the numbers become absurd. Even at 10% of light speed, which is far beyond our current capabilities, a generation ship would take 25 million years to reach Andromeda. 25 million years. That is roughly 1 million generations. 1 million generations of humans living on a single spacecraft, maintaining the technology, the social structures, the knowledge, the will to continue. Not for centuries, not for millennia, for millions of years. For a span of time greater than the entire existence of the genus Homo on Earth. The people who arrived at Andromeda, after 1 million generations of evolution and cultural drift in an enclosed, artificial environment, would bear little resemblance to the people who left. They might not even be recognizably human. They would have evolved, both biologically and culturally, into something entirely new. The generation ship would not deliver humans to another galaxy. It would deliver the descendants of humans, whatever they had become after 25 million years of isolation and adaptation. Another idea is cryogenic hibernation. Freeze the crew at the start of the journey, keep them in suspended animation for the duration, and thaw them out at the destination. This solves the problem of needing to sustain a living community for millions of years. You just need to keep the frozen bodies intact. But we do not currently have the technology to freeze a human being and revive them. Cryonics, the practice of freezing recently deceased people in the hope of future revival, is a real field, but the gap between freezing someone and actually bringing them back to life is enormous. When water freezes, it forms ice crystals that tear through cell membranes like tiny knives, causing massive cellular damage. Vitrification, a technique that turns biological tissue into a glass-like state without forming ice crystals, offers some hope, but it has only been demonstrated for small tissues and individual organs, not for entire human bodies. And even if we perfected the freezing and revival technology, the spacecraft carrying the frozen crew would need to function autonomously for millions of years. No known material can withstand millions of years without degradation. Metals corrode, polymers break down, electronic components fail. Cosmic radiation damages materials and corrupts data storage. Maintaining a functioning spacecraft for millions of years with no crew to perform repairs is an engineering challenge that makes freezing humans look easy by comparison. There is also the idea of digital consciousness upload. Instead of sending physical humans, you encode their consciousness, their memories, their personalities, as digital information and transmit it electronically. At the speed of light, a radio signal would take 2.5 million years to reach Andromeda. That is still enormously long, but it is the fastest possible method using known physics. At the other end, a receiver would decode the signal and reconstruct the consciousness, perhaps in a new biological body, perhaps in a robotic one, perhaps in a virtual environment. This approach has several problems, the most fundamental of which is that we do not know how to encode a human consciousness. We do not fully understand what consciousness is, let alone how to capture it, digitize it, and transmit it. Moreover, there is the deep philosophical question of whether a copy of you is really you. If your consciousness is transmitted, decoded, and reconstructed at the other end, Is the resulting entity you, or is it a copy? If the original you still exists at the sending end, there are now two of you. Which one is the real you? These questions touch on the deepest mysteries of personal identity and the philosophy of mind, and they have no easy answers. And there is the practical problem of needing a receiver at the destination. You cannot transmit a signal to Andromeda and have it reconstructed if there is no one there to receive it. Someone, or something, needs to have already gone there and set up the receiver. But how do you get the receiver there? You are back to the same problem of physically transporting something across millions of light years of space. Let me talk about some more exotic propulsion concepts that have been proposed for interstellar, if not intergalactic, travel. One of the most dramatic is nuclear pulse propulsion, the idea behind Project Orion, which was studied by the United States in the late 1950s and early 1960s. The concept was simple and brutal. Detonate nuclear bombs behind a spacecraft and ride the shock waves. A large pusher plate at the rear of the ship would absorb the energy from each detonation, and shock absorbers would smooth out the ride. Calculations showed that such a spacecraft could potentially reach 5 to 10% of the speed of light, making interstellar travel feasible within a few decades for nearby stars. But the Partial Nuclear Test Ban Treaty of 1963 effectively killed the project, since it prohibits nuclear detonations in space. And even at 10% of light speed, Andromeda is still 25 million years away. Antimatter engines represent an even more ambitious approach. When matter meets antimatter, they annihilate each other, converting 100% of their combined mass into energy, as per Einstein's E equals mc squared. This is the most efficient energy conversion possible, far more efficient than nuclear fission or fusion. A matter-antimatter engine could, in theory, accelerate a spacecraft to a significant fraction of the speed of light. But the practical obstacles are immense. We currently produce antimatter and particle accelerators at a rate of only a few nanograms per year, at a cost of tens of trillions of dollars per gram. Storing antimatter is incredibly challenging because it annihilates on contact with any regular matter. You would need to contain it in magnetic traps, completely isolated from the walls of its container, for the entire duration of the mission, and you would need tons of it for an intergalactic voyage. Even if we could somehow produce and store sufficient antimatter, and even if we could build an engine that could efficiently convert the annihilation energy into thrust, the time spans for intergalactic travel would still be millions of years. The Breakthrough Starshot Initiative, announced in 2016 with backing from the late Stephen Hawking and billionaire Yuri Milner, proposes a more near-term approach to interstellar travel. The idea is to use a massive ground-based laser array to accelerate tiny, gram-scale probes attached to light sails to 20% of the speed of light. At this speed, the probes could reach Proxima Centauri in about 20 years. This is an exciting and potentially feasible concept for interstellar exploration, but it does not help with intergalactic distances. At 20% of light speed, Andromeda is 12.5 million years away. And the probes are tiny, carrying at most a few grams of instruments. There is no room for passengers, no room for large scientific instruments, no way to decelerate at the destination. The probes would flash through the Alpha Centauri system at 20% of light speed, taking measurements as they went, and then fly off into the interstellar void forever. There is another concept called the Krasnikov tube, proposed by the Russian physicist Sergei Krasnikov. The idea is that a spacecraft traveling at near light speed through space could modify the spacetime behind it, creating a tube of distorted spacetime that would allow subsequent travelers to traverse the same distance at effectively faster than light speeds. The first ship does not travel faster than light. It makes the journey the hard way, at near light speed, taking years or decades. But it leaves behind a highway, a tunnel through space-time, that others can use to make the return trip or the same journey much more quickly. Like the warp drive and wormholes, the Krasnikov tube requires exotic matter and is purely theoretical. But it is an interesting variation on the theme of manipulating space-time to overcome the limitations of light speed. Now, there is one scenario for intergalactic travel that does not require any new physics at all. It does not require warp drives, wormholes, exotic matter, or any other speculative technology. It just requires patience, a lot of patience. About 4.5 billion years of patience, to be precise, because the Andromeda Galaxy is coming to us. Yes, you read that correctly. Despite the overall expansion of the universe, which is carrying most galaxies away from us, the Andromeda Galaxy is actually moving toward the Milky Way. The two galaxies are approaching each other at about 110 kilometers per second. This might seem to contradict what I said about the expansion of the universe, but it does not. The expansion of space is a large-scale phenomenon. On the scale of the local group, the gravitational attraction between the Milky Way and Andromeda is stronger than the expansion of space. The galaxies are close enough that their mutual gravity overcomes the cosmic expansion and pulls them together. It is like two people walking toward each other on a slowly expanding conveyor belt. If they are walking faster than the belt is expanding, they will still meet. In about 4.5 billion years, the Milky Way and Andromeda will collide, or rather, they will merge. Collide might be the wrong word, because it implies a violent crash, and the reality is more like a slow, graceful, cosmic dance. Galaxies are mostly empty space. The average distance between stars in a galaxy is several light years, and the stars themselves are tiny compared to those distances. When two galaxies merge, the vast majority of stars pass by each other without incident. There are no stellar collisions, or at least they are incredibly rare. What happens instead is a gravitational restructuring. The spiral structures of both galaxies are destroyed. Stars are flung onto new orbits. The combined galaxy settles, over billions of years, into a large elliptical galaxy. Astronomers sometimes call this future merged galaxy Milkomeda, and it will be our home galaxy for the foreseeable future. So, in a sense, we will eventually be part of an intergalactic encounter. We will merge with another galaxy. But we will not have traveled to it, it will have come to us. And we will not experience it in any dramatic way. Our solar system, if it still exists in 4.5 billion years, which is about the time the sun will begin to exhaust its hydrogen fuel and start expanding into a red giant, will simply find itself in a new galactic neighborhood, orbiting the center of a larger galaxy, under a sky full of different stars. It will be the most epic event in the history of our corner of the universe, and yet, if any beings are there to witness it, it will happen so slowly that they might not even notice. But here's the thing about the Andromeda merger. It is basically the only significant intergalactic merger we will ever experience. After the local group galaxies merge into one giant elliptical galaxy, the expansion of the universe will carry all other galaxies beyond the cosmic event horizon. Our merged galaxy will be an island in an expanding sea of emptiness, and it will remain so forever. We get one intergalactic encounter, one merger, one chance to experience another galaxy, and then the curtain comes down. The rest of the universe disappears over the cosmological horizon, and we are alone. Let me pause here and address something that I think is important. You might be wondering, at this point, whether there is any hope at all, whether we are destined to be trapped in our little corner of the cosmos forever, watching the universe expand away from us, unable to explore, unable to reach out, unable to even communicate with whatever is out there. And I want to be honest with you. With the physics, as we currently understand it, The outlook for intergalactic travel is bleak, not just difficult, not just impractical, but seemingly impossible. The speed of light, which is the fastest any object or signal can travel through space, is simply too slow to bridge the gaps between galaxies in a universe that is expanding faster than light can keep up. But I also want to say this. We are a young species. Human civilization is about 10,000 years old. Modern physics is about 400 years old. Quantum mechanics and general relativity are about 100 years old. We have been doing science, in the modern sense of systematic investigation of nature through experiment and theory, for an eye blink in cosmic time. And in that eye blink, we have gone from not knowing that other galaxies exist to photographing black holes in distant galaxies, detecting gravitational waves from emerging neutron stars, and landing robots on Mars. The pace of our progress is extraordinary. And while it would be hubris to assume that future discoveries will solve every problem, it would be equally foolish to assume that we have already discovered everything there is to know. We understand about 5% of the universe. 5%. Ordinary matter, the atoms and molecules and particles that we can detect and study, makes up a mere 5% of the total mass energy of the cosmos. 27% is dark matter, a mysterious substance that interacts gravitationally but does not emit, absorb, or reflect light. We have never directly detected a dark matter particle. We do not know what it is. We can see its effects on galaxies and galaxy clusters, and we can map its distribution through gravitational lensing, but its fundamental nature remains one of the great unsolved mysteries of physics. And 68% of the universe is dark energy, the even more mysterious force driving the accelerating expansion. We know essentially nothing about what dark energy is. It is the dominant component of the universe, and we are almost completely ignorant of its nature. When 95% of the universe is made of stuff we do not understand, it seems premature to declare anything impossible. Maybe dark matter or dark energy, once understood, will reveal new physics that changes the game entirely. Maybe there are phenomena at the intersection of quantum mechanics and general relativity in the still unformulated theory of quantum gravity that we cannot currently imagine, but that would open new possibilities for travel or communication. Maybe the extra dimensions predicted by string theory, if they exist, could provide shortcuts through space-time that we have not conceived of. Maybe the ER equals EPR conjecture, linking wormholes to quantum entanglement, will lead to breakthroughs that we cannot foresee. We simply do not know. And we do not know what we do not know. There is a beautiful concept in the philosophy of science called the adjacent possible. It was coined by the theoretical biologist Stuart Kauffman to describe how, at any given moment, there's a set of things that are just one step away from being discovered or created. The adjacent possible is the boundary between what exists and what is within reach of the next innovation. And the thing about the adjacent possible is that each time you step into it, each time you discover something new, the boundary expands. New possibilities open up that were not there before. The discovery of quantum mechanics opened up the adjacent possible of transistors, which opened up computers, which opened up the internet, which opened up artificial intelligence. None of these things were even imaginable before the preceding discoveries. Each one expanded the frontier of what was possible. So, when I say that intergalactic travel appears impossible with known physics, I am being honest about the current state of our knowledge. But I'm also aware that our knowledge is profoundly incomplete. I am aware that every generation of scientists has believed that they were close to a complete understanding of the universe, and every generation has been wrong. The history of science is a history of surprises, of paradigm shifts, of discoveries that nobody predicted and that changed everything. Who knows what surprises await us in the next century, the next millennium, the next million years? Maybe the answer is that intergalactic travel really is impossible. Maybe the cosmic speed limit is absolute and unbreakable. Maybe we are truly, permanently confined to our local patch of the universe. That is a real possibility, and we should be prepared to accept it if the evidence demands it. But maybe, just maybe, there is something out there that we have not thought of yet. Some piece of the puzzle that, once found, will transform the impossible into the merely very difficult. I do not know, and neither does anyone else. That uncertainty is not a weakness. It is the very essence of science. It is what keeps us looking, keeps us asking, keeps us exploring. Let me turn now to the James Webb Space Telescope, because I think it provides a beautiful lens through which to view our topic. Since its launch on Christmas Day 2021, and its deployment at the second Lagrange point about 1.5 million kilometers from Earth, JWST has been revolutionizing our understanding of the cosmos. Its infrared vision allows it to peer deeper into the universe than any telescope before it, detecting the faint red-shifted light from the earliest galaxies that formed in the first few 100 million years after the Big Bang. The images that JWST has produced are breathtaking. Deep field images show thousands of galaxies in a tiny patch of sky, each one a vast island of stars, each one at a different distance, a different epoch in cosmic history. Some are relatively nearby, their spiral arms clearly visible, their star-forming regions glowing in vivid detail. Others are distant smudges, their light stretched by billions of years of cosmic expansion, their colors shifted deep into the infrared. And a few are mere specks, almost invisible, the most distant galaxies ever observed, seen as they were when the universe was a fraction of its current age. One of the most remarkable discoveries JWST has made is that galaxies formed earlier and grew larger faster than our models predicted. Galaxies that existed just a few 100 million years after the Big Bang are more massive, more luminous, and more structurally complex than our theories said they should be. This does not overthrow the basic framework of cosmology, but it does suggest that there is something about the process of galaxy formation that we do not fully understand. The early universe was apparently more productive, more efficient at building galaxies than we gave it credit for. This is the beauty of observational science. The universe always has surprises in store. But here is the poignant irony of JWST's discoveries. Every galaxy it reveals, every new record-breaking observation it makes, is a galaxy we will never visit. Many of the galaxies in JWST's deep field images are already beyond our cosmic event horizon. The light we are seeing left them billions of years ago, when they were close enough for their light to eventually reach us. But the galaxies themselves, as they exist today, are billions of light years farther away, receding at speeds exceeding light. They are ghosts, beautiful, informative, scientifically invaluable ghosts, but ghosts nonetheless. We can study them, we can learn from them, we can marvel at them, but we can never meet them. JWST is, in a sense, the ultimate expression of the human condition in a vast universe. It extends our sight but not our reach. It expands our knowledge but not our dominion. It shows us the universe in all its beauty and complexity and vastness, and in doing so it reminds us of how small, how brief, how local we are, and I think there is something profoundly valuable in that reminder. Not because it should make us feel insignificant or depressed, but because it should make us feel grateful. Grateful that we exist at all, in this particular moment of cosmic history, when the universe is still revealing its secrets. Grateful that we have the intelligence and the curiosity to build telescopes and ask questions and seek understanding. grateful that we are made of the same stuff as those distant, unreachable galaxies, that we share a common origin in the fires of the Big Bang, and that in some profound sense, their story is our story. Now, I want to talk about something that connects beautifully to our main topic, the Fermi paradox. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to the possibility of extraterrestrial life. Given the vast number of stars in the galaxy, the vast number of planets around those stars, and the billions of years that have been available for life to develop, it seemed statistically likely that intelligent civilizations should exist elsewhere in the Milky Way. If even a small fraction of those civilizations developed interstellar travel, they should have been able to colonize the entire galaxy in a relatively short time, maybe a few million years, a cosmically brief period. And yet, we see no evidence of their existence. No alien spacecraft, no alien signals, no alien megastructures. As Fermi reportedly asked, "Where is everybody?" This is the Fermi paradox, and it has dozens of proposed solutions, ranging from the mundane to the exotic. But the one that is most relevant to our topic is this. Maybe interstellar and intergalactic travel is just too hard. Maybe the speed of light really is an unbreakable barrier, not just in theory but in practice. Maybe no civilization, no matter how advanced, has figured out how to cross the vast distances between stars and galaxies in any practical way. Maybe the universe is teeming with intelligent life, billions of civilizations on billions of planets around billions of stars in billions of galaxies, and every single one of them is trapped. Stuck in their own solar system, or at best their own small corner of their galaxy, unable to reach out, unable to explore, unable to communicate across the immense gulfs of space. The universe might be full of brilliant, curious, yearning civilizations, all looking up at the same stars, all wondering the same thing. Where is everybody? This possibility is sometimes called the Great Filter, the idea that there is some barrier, some obstacle, that prevents civilizations from becoming interstellar or intergalactic. The filter might be behind us, something in the development of life or intelligence that is incredibly unlikely, making advanced civilizations extremely rare. Or the filter might be ahead of us, something that destroys or limits civilizations before they can spread among the stars. The speed of light and the expansion of the universe might be that filter. Not a dramatic catastrophe, not a self-inflicted apocalypse, but a quiet, implacable, mathematical impossibility. The universe might not need to destroy civilizations to prevent them from spreading. It just needs to be big enough and to be expanding fast enough that no civilization can overcome the distances. There is a related concept called the Kardashev scale, proposed by the Soviet astronomer Nikolai Kardashev in 1964. It classifies civilizations based on their energy consumption. A Type 1 civilization harnesses all the energy available on its planet, about 10 to the 16th power watts for an Earth-like world. A Type 2 civilization harnesses all the energy of its star, about 10 to the 26th power watts, perhaps by building a megastructure called a Dyson sphere around it. A Type 3 civilization harnesses all the energy of its galaxy, about 10 to the 36th power watts. Humanity is currently about a Type 0.7 on this scale. We do not even fully harness the energy of our own planet yet. The question that haunts our topic is this. Even a Type 3 civilization, one that commands the energy of an entire galaxy, might still be confined to that galaxy by the speed of light and the expansion of the universe. You can have all the energy in the galaxy, and it still is not enough to overcome the expansion of intergalactic space. The cosmic speed limit does not care how advanced you are. The expansion of space does not care how much energy you have. The laws of physics apply equally to bacteria and to gods. And if those laws say you cannot cross the intergalactic void, then you cannot cross it, regardless of your technological sophistication. Some have speculated that there might be a Type 4 or Type 5 civilization, one that has somehow transcended the limitations of a single galaxy and commands the energy of multiple galaxies or even the entire universe. But this is pure speculation, with no physical basis whatsoever. And the whole point of our discussion is that the physics of the expanding universe seems to actively prevent any civilization from reaching this level, because the raw material, the energy, the galaxies themselves, are being carried away faster than they can be collected. There is another possible response to the Fermi paradox that I find compelling and slightly melancholy. Maybe advanced civilizations, upon realizing that intergalactic travel is impossible, turn inward. Instead of trying to spread outward into a universe that is running away from them, they focus on making the most of what they have. They explore the inner worlds of consciousness, of virtual reality, of mathematics and art and philosophy. They build not outward, but inward, creating rich, complex, beautiful civilizations within the confines of their own solar systems or galaxies. They accept the cosmic speed limit not as a tragedy but as a boundary condition, and they find meaning and purpose within those boundaries. Maybe the universe is full of these civilizations, thriving and contented, but invisible to us because they are not trying to communicate across the voids of space. They have accepted their cosmic solitude and found peace in it. I find this possibility somehow comforting. Not because I want us to give up on exploration, but because it suggests that limits do not have to be defeats. Boundaries can be liberating. Knowing what you cannot do can help you focus on what you can do. And what we can do even within the confines of our one small planet orbiting one small star in one medium-sized galaxy is extraordinary. We can build telescopes that see 13 billion years into the past. We can decode the fundamental laws of physics. We can compose symphonies and write poetry and create art that captures the beauty and terror of the cosmos. We can love each other, care for each other, build communities and cultures that enrich the experience of being alive. We are the universe becoming aware of itself, and that awareness is not diminished by the fact that we cannot travel to every corner of ourselves. Let me come back now to some hard science, because there are a few more aspects of this topic that I want to explore in depth. I want to talk about the mathematics of unreachability, because I think the precision and certainty of the math drives home the point in a way that words alone cannot. The key concept is the distinction between different ways of measuring distance in an expanding universe. In everyday life, there is only one kind of distance, the distance between 2 points, measured with a ruler. But in cosmology, things are more complicated, because space is expanding. The distance between two objects changes over time, even if neither object is moving through space. So, which distance do you mean? The distance right now, the distance when the light was emitted, the distance when the light arrives. These are all different, and they can differ by enormous factors. Co-moving distance is the distance between two objects measured at the present time, accounting for the expansion of space. It is the distance you would measure if you could somehow freeze the expansion of the universe and lay a giant ruler between the 2 points right now. For the most distant galaxies we can see, the co-moving distance is about 46.5 billion light-years, even though the light from those galaxies has only been traveling for about 13.5 billion years. The difference is entirely due to the expansion of space. While the light was traveling toward us, the space it had already traversed was stretching, and the galaxy it came from was being carried farther and farther away. By the time the light arrives, the source galaxy is much farther away than the distance the light traveled. Proper distance is similar to co-moving distance, but accounts for the scale factor of the universe at a specific time. It is the actual distance between 2 points at a given moment, not the distance that light has traveled. The proper distance to a distant galaxy right now is its co-moving distance. The proper distance when the light was emitted was much smaller. The proper distance changes over time as the universe expands. Light travel distance, also called look-back distance, is the simplest to understand. It is simply the distance that the light has traveled, which equals the speed of light times the travel time. For a galaxy whose light has been traveling for 13 billion years, the light travel distance is 13 billion light years. But the actual current distance to that galaxy is much larger, about 30 billion light years or more, because of expansion. These distinctions matter enormously for our topic, because they determine what is reachable and what is not. The cosmic event horizon, the boundary beyond which light emitted today will never reach us, is defined in terms of co-moving distance. Its current value is about 16 billion light years. Any galaxy with a current co-moving distance greater than about 16 billion light years is permanently beyond our reach, and light we emit today will never reach it. But the observable universe has a radius of about 46.5 billion light years in co-moving distance. This means that we can see galaxies that are currently up to 46.5 billion light years away. But we can only reach galaxies that are currently less than about 16 billion light years away. The vast majority of the observable universe, about 97% of all galaxies we can see, is already beyond our cosmic event horizon. 97%. We can see them, but we can never reach them, never communicate with them, never send a probe to them. They are visible, but untouchable. Present, but absent. Real, but forever inaccessible. And this fraction is growing. As the expansion accelerates, the cosmic event horizon shrinks in co-moving coordinates, and more galaxies pass beyond it. The number of reachable galaxies is decreasing with every passing moment. Right now, there are galaxies on the edge of our event horizon, sending us their last photons. Light that left them recently will still reach us, but light they emit in the future will not. They are in the process of disappearing, of fading out of our reachable universe, and there is nothing we can do to stop it. The mathematical framework that describes all of this is Einstein's general theory of relativity, specifically the Friedmann equations, which describe the dynamics of a homogeneous, isotropic, expanding universe. The Friedmann equations relate the rate of expansion of the universe, quantified by the Hubble parameter, to the density and pressure of the matter and energy it contains. In a universe with matter, radiation, and dark energy, these equations predict a specific expansion history. A rapid initial expansion, a period of deceleration as matter and radiation dominate, and then an accelerating expansion as dark energy takes over. This prediction matches our observations with remarkable precision. The Friedmann equations, combined with measurements of the cosmic microwave background, the distribution of galaxies, and the distances to Type 1a supernovae, give us a detailed and consistent picture of a universe that is expanding at an accelerating rate, with a cosmic event horizon that is gradually cutting us off from the rest of the cosmos. There is a quantity in cosmology called the scale factor, usually denoted by a lowercase a, which describes how the size of the universe changes over time. If you normalize the scale factor to 1 at the present time, then a scale factor of 1/2 means the universe was half its current size, and a scale factor of 2 means it will be twice its current size. The scale factor increases monotonically in our expanding universe, and the rate at which it increases is governed by the Friedmann equations. In the far future, as dark energy dominates, the scale factor will increase exponentially. This exponential growth is what drives the accelerating expansion and what makes the cosmic event horizon shrink. The mathematics is clear, precise, and unforgiving. It tells us that we live in a universe that is, in a very real sense, dissolving around us. The galaxies are being carried away by the expanding fabric of space, like islands drifting apart on a rising sea. And the speed of light, the fastest messenger the universe provides, is not fast enough to bridge the growing gaps. This is not a failure of technology or imagination. It is a feature of the geometry of space-time itself. It is built into the equations. It is part of the architecture of reality. I want to share something with you now that I think adds an important layer to this discussion. It is the Hubble tension, and it is one of the most exciting and puzzling problems in modern cosmology. As I mentioned earlier, the Hubble constant, the rate of expansion of the universe, has been measured using two fundamentally different methods, and the two methods give different answers. Measurements based on the cosmic microwave background, using data from the Planck satellite, give a value of about 67.4 kilometers per second per megaparsec. Measurements based on nearby supernovae and other local distance indicators give a value of about 73 kilometers per second per megaparsec. The discrepancy is about 8%, which might not sound like much, but the measurements are so precise that the probability of this discrepancy being due to random error is extremely small. Something is going on. Either one or both of the measurements has a subtle systematic error that has not been identified, or the two methods are measuring something slightly different, or there is new physics at work that our current models do not account for. If it is new physics, the implications could be profound. The Hubble tension might be telling us that the expansion of the universe is not exactly what our standard model predicts. Maybe dark energy is not constant. Maybe it changes over time. Maybe there are additional particles or forces that we have not accounted for. Maybe the universe is slightly different from what we think it is. The resolution of the Hubble tension, whatever it turns out to be, will deepen our understanding of the universe, and it might change the numbers in our cosmic accounting. It might make the event horizon slightly larger or slightly smaller, the expansion slightly faster or slightly slower, the future of the universe slightly different from our current projections. But it is unlikely to change the fundamental conclusion. The speed of light is too slow to reach other galaxies. The discrepancy is at the level of a few percent, while the problem of intergalactic distances is at the level of factors of millions and billions. The Hubble tension is a fascinating puzzle, but it will not save us from the tyranny of cosmic expansion. Now, let me take you even deeper into the cosmic timeline, because I think understanding the deep future of the universe adds a profound and meditative dimension to our topic. We have talked about what will happen in the next 100 billion years or so. The disappearance of all galaxies outside the local group beyond the cosmic event horizon, the merger of the local group into a single large galaxy, the isolation of that galaxy in an empty expanding void. But what happens after that? What is the ultimate fate of the universe? The current best evidence supports a scenario called the heat death of the universe, also known as the Big Freeze. In this scenario, the universe continues to expand forever at an ever-accelerating rate. As it expands, the density of matter and energy decreases. Stars exhaust their nuclear fuel and die. The last stars, tiny red dwarfs burning their hydrogen with miserly efficiency, will wink out in about 100 trillion years. After that, the universe will contain only the cooling remnants of stars. White dwarfs slowly cooling to black, neutron stars fading, black holes slowly evaporating through Hawking radiation. The temperature of the universe will asymptotically approach absolute zero, but never quite reach it. In this cold, dark, almost perfectly empty universe, nothing of interest will ever happen again. The entropy of the universe will have reached its maximum. All energy will have been dissipated, all gradients smoothed out, all structures dissolved. This is the heat death. Not a dramatic explosion or collapse, but a slow, quiet, eternal fading into cold darkness.